All right, today we're learning about parametric calculus, and we're getting started with day one. And before we get started, the trivia question for the video is, we have a electron microscope scan of a substance or material, object, whatever you want to call it, right here. And the trivia question is, what is it? I'll give you a hint. You'll find it in some classrooms. All right, in this video we're going to learn how to sketch parametric curves, and we are going to both sketch by hand, and we are also going to use a calculator to help support and confirm what we sketched by hand. But before we get to sketching parametric curves, perhaps we should talk about what a parametric curve is. Typically, we have been working with functions, and functions trace out a curve for us. However, not all curves can be traced with a function. For example, if you were riding on a whirligig here and at the carnival, and you're sitting here in the car, what's happening is you're spinning around in circles, and this whole bar is spinning around, and so you might get a path which looks very non-function-like. That might look something like this. And that doesn't exactly, or that is not representable by a function, but we still can talk about your movement. For example, at certain times you might be moving to the left, and other times you might be moving to the right, and sometimes you're moving upward. And we want to be able to talk about the calculus of that path. So parametric curves are a tool for looking at more complicated paths. And the other examples here are, for example, a fly. It's got a very erratic flight pattern, or maybe you've got a robot that's moving to avoid obstacles, or even a rock stuck in a rolling tire, and what is the path of that rock? You've got this smooth curve, and then it comes to a point, and then it repeats the pattern, and that pattern is not easy to represent with a function, but it's fairly easy to represent with a parametric curve. So let's talk about parametric curves. When we're dealing with functions, we're often dealing with y equals f of x, and with a parametric curve we actually break down into two variables. You have your x movement, the left-right movement, and you have your y movement, the up-down movement. And then we introduce a third variable, which is called the parameter. The parameter is typically going to be a t or a theta, and each separate equation using that parameter is called a parametric equation. So without further ado, let's look at example 1. All right, without a calculator, make a table and sketch the indicated curve. Be sure to indicate the direction of your graph. So let's zoom in on this table here, and what we're going to do is first we're going to graph each variable on its own, and then we're going to graph the relationship of them. So the first variable we want to graph is x, and they give us the time interval of -2 to 3. So in my table I'm going to write the time interval -2 to 3. And then what I want to do is start evaluating this for the x-coordinate. And the x-coordinate is given as t squared minus 4. So if we plug -2 into that, we're going to get -2 squared minus 4 is 0. And then we plug -1 into that, and we get 1 minus 4 is -3. And we continue down the table filling out the values. And 3 squared minus 4 is 5. All right. If we were to sketch a graph of that curve, our input variable was time, and our output variable was the x of t. And we want to graph this. So it looks like our time goes to -2 and up to 3. And we'll just call out our x values, 1, 2, 3, 4, 5. And we start plotting our points. So our first point is at -2, 0. Then we have a point at -1, comma, -3, then a point at 0, comma, -4, and we wind up plotting all our points, 1, 2, 3, 4, 5. And we get this curve which probably does something very parabola-like, which is supported by the fact that we have a parabola curve. I'm going to put in some arrows here to indicate the direction that traced out in. So as we moved forward through time, the x-coordinate dropped in value and then it increased in value up to 5. Doing a table for the y value, what we can do is we can plug -2 into our y equation. So -2 divided by 2 is -1, and -1 divided by 2 is -1/2, 0, 1/2, 1, and looks like 3/2. So our y-coordinate is going to be changing. It looks like it's increasing. I'm going to slide over and graph that. So as we graph our y values, our input variable again is time, and our output variable is y of time. And we'll put some tick marks on our graph, and we plot the points. The first point occurs at -2, comma, -1. Then we have one at -1, comma, -1/2. And as we plot out these points, it looks like we have what appears to be a straight line, which fits with our equation y equals t/2. So a straight line with a slope of 1/2. Okay. Now we want to do what is the parametric curve, and the parametric curve is where you take these two curves and combine them. So what's going on is I'm going to use these as my coordinates that I'm mapping out, and I'm going to graph my x along the horizontal axis and my y along the vertical axis. So sliding to the third graph, let's do this in black. Our input, our x variable goes along horizontal and our y variable goes along the vertical, and we start plotting the points. Let's put some tick marks down here. 1, 2, 3, 4, 1, 2, 3, 4, 5. All right, our first coordinate occurs at 0, comma, -1. And then we have a point at -3, comma, -1/2. And we have one at -4, 0. And then one at -3, comma, 1/2. One at 0, 1. And finally the last one at 5, 3/2. And here we go. The curve sweeps out like that. And we'll put some direction arrows on there to show the direction that the curve traced out on. And those direction arrows will help us when we get to analyzing things like calculus. With this arrow we can tell that at time 4 the particle was moving in a, or sorry, not time 4, that's time 0. At time 0 the particle was moving in an upward direction, and it was changing from left to right. Okay, there's graphing a parametric curve, and I'm going to walk us through how to do this with a calculator. So let's open up a calculator program. Grab your calculator. Okay, let's assume that I wanted to verify my findings with my calculator. So what I've got here is the calculator, and I'm working in parametric mode. So the first thing I want to do is make sure that I am in parametric mode. So I press the mode key, and I'm going to scroll down until I get to my function, and then I'm going to highlight parametric mode, and I hit enter. And what that does is it enables me to enter information in a parametric mode. So the first thing I'm going to do is I'm going to enter in my two equations. So I can press the y equals here, And as you can see, the grapher now has a slightly different looking function, and you have a x1 in terms of t and a y1 in terms of t. So under my x1, I'm going to type in t squared minus 4. And as you notice, when I press the x key, the t shows up. So t squared minus 4. And then I'm going to scroll down to my y1, which I have as t divided by 2. And the first thing I want to do is I want to check my table. So I'm going to check my table setting. And the way we can do that is we can go to Second Table Set. And we are starting, our table value starts at a value of -2. And for the notes, we were stepping by a distance of 1. So this should give us a table, and we can go to our table by pressing Second Table or Second Graph. And we see in this table here, the values match up with our findings. And that's excellent. And we want to now confirm our graph. So we need to check our window setting first off. And so to do that, we press Window. And we see a new setting here, Tmin, Tmax, and Tstep. So for us, our T minimum was -2, so we'll put in -2. Our T max was 3, and the time step, or the T step, we could go by intervals of 1, but I'm going to set this at a 0.1 so that we can watch it trace out. And after this, we can press Graph, and we see the drawing has traced out. And not only that, we see it started at this point and it swept to the left and then came back to the right and finished right there, confirming the graph that we drew in the third box. All right, I'm going to toy around with the windows here so we can explore what happens. It looks like the smallest value we have is -4 and the largest is 5. And we also are pinned between -1 and 2. So let's change our window just a little bit. We'll put our x minimums to, we'll go -6 to 6. So we're basically zooming in on this. And then our y min and max will change to, we'll go -3 to 3. And doing that allows us to have a slightly more zoomed in graph. I also want to explore what happens if I change the window setting of the T-step. So let's scroll down and change our T-step to, we'll do what the table said, just a straight up 1. And if we hit Graph, what we see is it plots the first point and then draws a straight line to the second point and then a straight line to the third point, 4, 5, 6. So the table step, or our T-step, changes fidelity. If I changed it to like 0.01, it's going to trace out slower, but we'll get a more accurate curve because it's plotting a point at every 0.01 T values. All right. Let's take a look at removing the parameter, and then we're going to come back and do a few more graphing exercises. All right, we have the two equations x and y, and when we remove the parameter, we are trying to express it as a function, either a function in y or a function in x. And it's not always possible to remove the parameter, and when we remove the parameter, we lose some information, and we'll talk about that on the next page. But the way that I go about removing the parameter is I pick whichever equation is easiest to solve for t. And in this case, it looks like the bottom equation is easiest to solve for t. And I get 2y is equal to t. And once I have it solved for t, I'm going to plug that value in to my other equation. And so what we'll wind up getting is x is equal to 2y squared minus 4. And now we have removed the parameter. We have an answer that is in terms of x and y, so there is no parameter. And we can see, for those who are comfortable with their transformations, that what we have is the function that is graphed out above. We have something that is shifted to the left 4 units, and remember this is in terms of a function of y instead of a function of x. And there's been a horizontal compression by 1/2, and overall it's a parabola. So we've got this parabola that starts shifted left to the right, or to the left 4 units. In losing the parameter, what we see is we no longer can see where the curve starts or where it finishes at. So the parameter is an important feature because it tells us the start point and the finish point. Also, it's an important feature because it tells us the direction that we are traveling in. So we won't do this too often where we remove the parameter, but sometimes it helps us confirm that we've graphed the drawing correctly. All right, let's graph the next couple curves that our notes are asking us to graph and have a conversation about those. Okay, so our notes are asking us to examine 2 other curves, and let's take a look at this in the calculator. The first curve, our x value has changed to 4t squared minus 4. So we'll type that in, 4t squared minus 4. And our y value has changed to just t. And they also give us a t step, so we're going to change our window. The t step we'll leave at 0.01, but our min and max is changed to -1 up to 1.5. And let's go ahead and graph that curve now. And what we see here is a curve which pretty much resembles the first curve as far as I can tell. It looks like it started at the same point and it moved to the left and then came back towards the right as it was moving upward. Let's try the second curve that they ask us to look at. The first equation, x of t, is 4 parentheses 2 sine t, close parentheses, plus 1, close parentheses, squared, minus 4. And the second equation is 2 sine of t plus 1. And again, we need to make sure that we use the same t interval. So we're going to go to our t windows, and it looks like the t min, they want us to put negative 1.571 and go to a, I bet you I used the minus. Yep, I used minus instead of the negative. There we go. And the maximum 0.253. 0.253. All right, and we hit graph. And this seems to be drawing the same curve. However, it appears to be going at a much slower pace as it works through the curve. So there might be something to be learned from that. Okay, let's talk about what we learned there. So rectangular equations, the y equals f of x equations, they allow us to see what the curve looks like, or we can see the path that the particle is moving. But parametric equations, they give us more information. They not only show us the path, but as we saw, I drew direction arrows on there, so it also tells us the direction, and with some calculus we might be able to evaluate the speed of the path. So I heard one person once refer to a function tells us it's like coming across a snowmobile track in the snow, and you can tell that a snowmobile went by, but having the parametric equations is akin to actually seeing the snowmobiler, because you're seeing them lay down the path, you're seeing the direction they're moving in, and you're seeing the speed that they're going. And when you break something down like that, you wind up having a lot more information that you can talk about rather than just the shape of the curve. You can talk about how quickly is it moving in the vertical direction, or how quickly is it moving in the horizontal direction. When is it at rest in the x direction, or when is it at rest in the y direction? So let's take a look at example 2 and see if we can draw some connections between our x of t, y of t, and the parametric curve. All right, I'm going to largely leave this as an exercise to the viewer, but I will walk you through one analysis here. What we're doing is we want to connect our x and y graph to one of our parametric graphs. And in this case, I see that my x value from time 0 to 1 is pinned between 1 and 2. So what I want to do is I want to look for a graph that is pinned between 1 and 2 on the x thing, so on the x-axis. Graph 1 doesn't work because it looks like it's pinned between negative 2 and 2. Graph 2 is pinned between negative 2 and positive 2. Graph 3 appears to be pinned between 1 and 2, so that looks like a good possibility. And again, graph 4 goes from negative 2 to 2. So I'm thinking it's probably graph 3, just based on x of t. Let's take a look at what y of t does. Looks like y of t starts at 0, and then it goes up to 1, down to negative 1, and then back up to 0. So we need a y value that starts at 0, goes up to 1, looks like we've got that going on here, up to 1, down to negative 1, and then back to 0. So this graph confirms both x of t and y of t. So I would say that A matches with graph 3. And I will leave it to the viewer to decide what A, B, C, and D match with. So if you want to pause the video here and think through it, I will display the answers. So go ahead and pause. All right, these were my findings. B matched with graph 1, and that had largely to do with the fact that the x value goes up, down, and then back to the spot where it started. And we can see that our x value goes up, and then down, and then up, and then back down, and then back to where we started with graph 1. And then the y value is more erratic. It does 3 changes, so there's up, 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 and then back to where we started. Graph C I matched with the fourth parametric curve, and I did that largely because the y value was pinned between a value of 0 and 2, and our y value is pinned between 0 and 2 on this curve and this curve only. And that left me with D matching up with graph 2 by process of elimination, but one of the things that I noticed that helped confirm that is there's a steady state for our x-coordinate. It stays at a value of 2, and we have a steady state where our x-coordinate stays at a value of 2. Similarly, we also have a steady state of the y value to begin with, and the y value down here at negative 2, right here, and here. So if I was being super attentive, I might say that the graph started somewhere around here and was moving in this direction. All right. All right, thanks for watching the video. Hopefully after this you're able to use your calculator to graph parametric curves as well as create a table and graph the parametric curve by hand. To answer the trivia question, the everyday object found here, or the object found in a classroom, this is an electron microscope scan of chalk. Thank you for watching.